All right. To a different view. Let's bring the chat up. All right. Where's all my good chalk? Oh, guys, this is an emergency. We gotta have good chalk. Oh, here's some right here. See, oh, here's the good one. They can take them the good chalk here. I don't blame them. This feels different. See here. There we go. I don't blame them. It's good for them. They get to taste the sweet power of normal chalk. Okay. Well, we got that figured out. I don't have to go to my office. Here we go. Okay. Let's talk about section 11.7 maximum and minimum values. So section, this is 11.7. 11.8 is our last section in this chapter, and our second exam will cover chapters 10 and 11, but we won't be having our exam today, clearly, in lab. We'll have it next week. Okay. Did that work? Or?
We had the week after.
Okay.
Since this last week.
This last week. Oh, you're right. Yeah. Thank you. Yeah. Okay. So not next week, but the week after that, because of the due dates and whatnot. So yes, that works out for everyone better. You guys get more time to study. I get more time to grade and create the exam. It's a win-win situation. Okay. All right. So let's talk about maximum and minimum values here. Okay. So a function has a local maximum. A function f of x, y has a local max at some point in R2 in the domain if for every we have so this is basically saying that if you have a bona fide local maximum at AB, that all your other points will be less than or equal to that value in AB of f evaluated at the point AB. And it will have a local minimum if this is true. So this is basically the intuitive argument of we have a local minimum, meaning, okay, if it's really a minimum at AB, then f of AB is going to be less than or equal to all the other values of f of x, y. Okay. Okay, so then remember how we found in earlier calculus, if you had some f of x is equal to y, we took the derivative and we set it equal to 0 to find the critical points, which were the maximum and minimum values. All right. And then we had a second derivative test. We said that if this was greater than 0, you had a local minimum. And if you said that Local maximum. Did Dr. Zoller draw these out for you guys? Did you guys take calculus 1 and 2 with him? No, he took it in high school. Yeah, I took calculus with him, and it was. I really liked it when he drew this. What he did was he said, okay, second derivative test. When it's positive, you get a smiley face. This is a concave up, local minimum. Whenever you take the second derivative test, it's negative, concave down, local maximum. I like to remember it like that because it brings fond memories of me taking this course with Dr. Zoller. So this still applies to our multivariable situation. So f of xy has a local maximum at f of a, b. Also, if exists and set this equal to 0, and we set this equal to 0, and that'll allow us to find critical numbers, local maximum or minimum. And we will have something analogous to the second derivative test to allow us to determine whether it's a minimum or a maximum. So without further ado, let's do some example problems. Okay. Let's do f of xy is equal to x squared plus y squared. Minus 2x minus 6y. The next term is a plus 14. Yes. Okay. So we aspire to find what are the maximum and minimum values of this surface in R3. Well, as we mentioned before, this requires taking partial derivatives with respect to the two variables that define the function, x and y. So let's perform this. This is a 2x. That goes away. It becomes a minus 2. That goes away. That goes away. Right? And then this becomes a 2y. This goes away. This goes away. This becomes a minus 6. That goes away. Okay. Then, just like in Calc 1 and 2, we set these equal to 0 because these really are slopes. And we want to know when is the slope 0 because that's when you're having a curve up or down. Okay, good. And then let's solve. So then I get x is equal to 2 divided by 2, which is 1. And I get y is equal to 6 divided by 2, which is 3. Okay. All right. So then I got 1 and I got 3. But this is a surface in R3. I need an x, y, and a z to determine a point P in R3, right? So far we have these pieces of information, but we don't know z. How do we determine z? Yes, absolutely correct, Caleb. Plug that 1 and that 3 in for x and y respectively. And we'll find what z is. Okay, so this becomes 1 plus 9 minus 2 minus 18 plus 14. Okay, so this becomes minus 20, this becomes 10, so this becomes minus 10, and then when you do that, this becomes positive 4. So this should be a 4. All right. So we found our critical point in R3. it is either a local minimum or a local maximum at 1, 3, 4. So how do we determine whether it's a local minimum or local maximum? Well, if we want to do it just by hand and not graph it using a computer algebra system, what we can do is we can kind of try and get that equation to look like something in a standard form, okay? So notice that if I recombine these, I can get x squared minus 2x plus y squared minus 6y plus a 14. And I've suggestively placed some distance between some of those terms there. Why do you guys think I did that? Yes, sir. So we can complete the square. So what we might want to do is set the function equal to 0 and complete the square. So then what I can do is just send this over here. And then I can complete the square in this variable. Very good. One here. Add a 1 here. Then I got to complete the square in this variable. Add a 9 here. Add a 9 here. So then we can factor this into an x minus 1 quantity squared plus a y minus 3 quantity squared. All right. And this equals -4. Everything right so far that you guys can tell? Okay, no slip ups. So then just resolving, just getting everything set equal to 0. Here's our function. And we could just say that it's equal to f of x, y. So here's the argument. Since this quantity right here is always greater than or equal to what? Notice that any number, even if it's negative, once we square it, it becomes what? Yes, sir. So even when x is equal to 0, -1 squared is 2. Even when x is equal to like -5, -6 squared is positive 36, right? So also we can say that, well, that applied to this thing is also true, right? So our point at 1, 3, and 4, what do you think that implies? Because what would allow our x to be 1, our y to be 3, and eventually getting an output of 4? Noticing that our function would get an output of 4 only if this term and that term was 0, right? Meaning it was the smallest contribution to the function's range. Do you buy that? Okay. So that means after that point, all of the f of xy outputs will be greater than that. This 1, 3. Like that 4 is the smallest value you can have. What I'm trying to say is f of 1, 3 equaling 4, as we found, is the minimum output. Does that make sense? So for instance, let's pick like f of 0, 0, okay? This would become 1 plus 9, which is 10, plus 4, which is 14. Notice that that's much bigger than 4, right? So we've noticed that at 1, f of 1, 3 is actually the smallest output of the function. What is that like a characteristic hallmark sign of? A minimum. That's right, Caleb. Is that a beaver on your hat?
Yes, it is.
That's very cute. I just now noticed it. For a second, I thought it was like a turkey or something,
Yeah.
but no, it's definitely a beaver.
Does it make sense? Because I'm a turkey.
Oh, yeah. It looked like the turkey was holding on to like some type of ham or something. But no, that's just a beaver's tail. And I'm chronically sleep deprived, so I'm like seeing things. So we have found the minimum f of 1, 3 by that argument right there. By this argument here, we show that f of 1, 3 is actually less than or equal to all possible outputs f of x, y. You can even try it. You can pick some points and see what happens. You know, I picked 0, 0, which was easy. And I noticed that f of 0, 0 equaled 14. Instead of 4, it equals 14. So pick any points besides 1, 3, and you'll notice that, wow, it's outputting a value bigger than 4. So that makes sense when we graph this function in a beautiful computer algebra system like Maple. Okay, you get this thing right here. And this point, guess where it is at? You guessed it. It's located at 1, 3, and 4. What shape does that make? What shape does that make? Can you tell?
Some sort of parabola.
Correct. It's an elliptic
That's-
paraboloid. Yep.
Wasn't it?
Yeah. It's supposed to look like one. You know, think about it. If like I put some other part up here, it'll look like a football. So it kind of looks like an ellipse, and it also kind of looks like a parabola, depending on which cross section you look at. But of course, my drawing is terrible. I do not blame you guys for not being able to tell that that is an elliptic parabola. Okay, let's continue here. Let's discuss the second derivative test for multivariable calculus. Okay, so your second partial derivatives on f have to be continuous. All right. And so do your first partial derivatives. So once your second partial derivatives and your second partial derivatives exist and are continuous, our second derivative test is this quantity, some d, which is a function of, when we evaluate it at a, b, all right? A, b are like fixed values. So it equals this. One way to remember this thing is that D is the determinant here. Oh, this needs to be here. Clairaut's theorem tells us that f of yx is equal to f of xy, given the conditions of Clairaut's theorem. So when you calculate the determinant, this becomes this. Minus the whole evaluated AB part. Okay, now that we got what the second derivative test is, has a good name because it has second derivatives in it. How do we use the test? Well, there's a few cases. What if D is positive? You got the value for D being positive and your double X derivative is positive. Clearly, this is at some point A, B, right? Maybe I should just. We're trying to see whether it's a minimum or a maximum, or as you will see, possibly neither. Is that f of x y squared? F of x y squared. This is f of x y squared over here. Right here. Same as right here. This right here is f of xy. This is f of yx. And this is f of yy. Clairaut's theorem tells us that f of yx is the same thing as f of xy, so that's why we put the square here. Okay. So now over there, this implies that we got a local minimum. There's case 2. Oh, wait, nope. Sinus split. Greater than 0. And your second partial with respect to x again is less than 0. All right. This implies we got ourselves a local maximum. And there's actually, believe it or not, a case 3. Notice here D is positive in all these. But over here, D will be negative. This implies a saddle point. And that actually means neither. Why? Why? Well, really got to kindle some artistic abilities here. Let's draw a saddle. All right. Okay. So notice that if you just travel in the y direction, this point seems like a local maximum right here. If you just travel across the y, you go, woo, oh, I'm at the top, and I'm going down. That must have been a local maximum. So our point of interest right here. I'm saying as you travel along the y, you travel along the saddle, it thinks that this is a local maximum when you travel across y. But interestingly enough, if you travel across x, it thinks that point is a local minimum. Yeah, my x should probably be a little bit more like, my x-axis should probably be more like, oh, and the axis needs to be straight, so like that. Now it's probably better to see that. Traveling across the x-axis, this point thinks, oh, hey, I went down, now I'm going back up. I'm pretty sure this is a local minimum. So the y thinks it's a maximum, the x thinks it's a minimum. They disagree. So this means this is a saddle point, and this is what occurs when d of AB, recall, d of AB, this is what happens when d of AB is negative, where d of AB is defined to be this. All right, so let's do some problems here. Let's classify some critical points. Let's find local minimums and local maximums or saddle points, if any, of some function f of x y is equal to x to the fourth, y to the fourth. Oh, that's a plus one. Okay. So our second derivative test might come in handy to determine and classify critical points. First, let's find the critical points, right? Like, what is that A, B? The A comma B are the points of interest that we want to see whether they're critical points. In the second derivative test, you need to plug in a critical point, right? Or else your second derivative test outputs misinformation, right? That it's supposed to test your critical point and tell you it's a maximum, it's a minimum, or it's a saddle point. So first we must determine the critical points, and that is doing the first partials and setting it equal to 0. So this is 4x cubed plus 4y. We're going to take partial x. So that goes to 0. That goes to 0. And then this becomes 4y cubed. That goes to 0. This becomes plus 4x. That goes to 0. All right. We need to solve these. What we can do is factor out a 4 and divide both sides by 4. And we get this. Right? So this is just begging us to solve for x over here. Right? So why don't we just plug that in over here? If y is equal to negative x cubed, then I get this. Right? So that becomes negative x to the 9th plus x. Is equal to 0. So we can factor out an x common term. Get that, can't we? Right. Also, we can factor out a negative and get rid of it. Right there. We're going to have to delete this info. We're running out of board space. We have it in our book and we have it in our notes. So over here, I can set negative x equal to 0. This implies x is equal to 0. And then I can set that x to the 8th minus 1 equal to 0. Your book decides to factor this and go crazy with it, but that's not necessary. Just add a 1 to both sides and take the 8th root. Take the 8th root of 1, which is what? Are you sure? It's just 1?
Yeah.
Whenever you take an eventh root, like a square root, you get plus or minus your thing. If you take a 4th root, you get plus or minus your thing. If you take a square root, you get plus or minus your thing. So actually, an 8th root gives you plus or minus 1. Because technically it satisfies the definition, because positive 1 to the 8th is 1, and negative 1 to the 8th is 1. So we get x is equal to 0, x is equal to negative 1, and x is equal to positive 1 as our roots. Okay. So if that's the case, then what is y? For each corresponding x, what is the y? Okay, so we have to determine it. If x is equal to 0 here, what is y? Y is negative x cubed. All right, so this implies y is negative 0 cubed, which is 0. So that means one of our points is 0, 0. This implies y is equal to negative 1 cubed, which is negative 1, which is 1. So one of our points is now negative 1, 1. And this implies y is equal to negative 1 cubed, which is just negative 1, which implies one of our points is 1, negative 1. Does that make sense how I did that? Something messed up here. Something messed up here. I got x equals 0, 1, and 2. X equals 0, 1, and negative 1. So then for 0, I get 0, 0. For 1, I get y. 1 cubed y should be negative 1. We get this, don't we? Y is equal to negative x cubed, right? So y is equal to negative 1 cubed, which is negative 1, which is positive 1. 1. Oh, I know why. Oh, I I'm plugging it into the derivatives, not into the original function. That's why it's going wrong. Okay. Oh, wait a second. Am I looking at the wrong question? Start here. Okay. Go to here. So I agree that it's x is equal to 0, 1, and negative 1. All right. Then I get 0, 0, but the book is getting 1, 1, and negative 1, negative 1. So are they using this equation? If we use this equation to solve for y, that means that's not a good one, because I would get y cubed is equal to negative x. I'd have to take the cube root. So I get y is equal to negative x. So they're using this equation right here. That must be it, because when they plug in a 0 for x, they get y is equal to 0. When they plug in a negative 1 for x, they should be getting a positive 1. I'll have to look into that. I'll have to look into why they're getting those results. Okay, we got x cubed minus y, x cubed minus y. Oh, setting these partial derivatives. Why is it? Oh my goodness. Oh, I copied the problem down wrong. That's why. I copied the problem down wrong. So there was a minus there, not a plus. So then retracing our steps, guys, I'll just retrace it in yellow, just so it's much more apparent. This needed to be a minus, meaning this is 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 a plus. And then meaning that y cubed is equal to x, okay, which is, all right, y cubed is equal to x, take the cube root, we get, over here we get y cubed is equal to x. Okay, that's what's going on here. Make sure you write down the problem correctly. Note to self and to you guys. So then when you take the cube root, x. Now it makes sense as to why they were getting what they were getting, okay? Let's redo this part real quick. All right. When I plug in a 0 in for x, I get y is equal to 0 cubed, which is 0. So one of the points is 0, 0. When I plug in a negative 1 for x, I get y is equal to a negative 1, all of it cubed, which is a negative 1. So that means I get negative 1, negative 1. Aha. And then I get y is equal to, when I plug in a positive 1 for x, 1 cubed, which is 1. So we get the point 1, 1. Does that make sense, guys? Yeah, I just put the wrong sign in the function. My function was right. Their function is right. We're just talking about a different function. So we're going to get different results. Okay. So we got that much covered. So we know those 3 coordinate pairs will be all the possible critical locations. Now, to do the second derivative test, okay, what do the equations on the right indicate? These guys, these indicate when I plug in x equals 0, -1, and 1 into this equation. So they indicate the critical points. These guys, this is a second derivative test. So we're actually going to use that now because we're going to take another partial derivative, which is a partial derivative of this guy again. So partial derivative of that guy again is going to be 12x squared, and the y goes away. Partial derivative of this guy, that's going to be 12y squared, with the x's going away. And then the mixed partial. We just need to calculate one mixed partial. So let's take the derivative of this guy, it doesn't matter. Respect to y, the derivative of this becomes -4. Notice that we could have picked this guy. The derivative with respect of this is also -4. Okay. So the second derivative test at any of our desired points will tell us what we have. So let's pick 0, 0. Okay. So what is d of 0, 0? All right. That's f of double here. Right. So let's evaluate. What happens when I plug in zeros here? I get a 0. What happens when I plug in zeros over here for x and y? I get a 0. So all that matters is what is this term doing? Notice this term has no x or y in it, so it's always -4 squared. So this becomes a 16 with the minus sign out in front of it. So d of 0, 0 is negative. And if we go back to our theorem that tells us about the second derivative test, okay, if d is ever at all negative, then you have a saddle point. So at 0, 0, we have a saddle point. What about at the other one? Let's check for the other ones. I gotta delete this stuff right here. So this is saddle point right here. What about -1, -1? What is d of -1, -1? Well, that's this. So let's plug a -1 in here for x. I get -12. Oh no, over here, when I plug in -1 for x, it gets squared, so it becomes a +1. So this becomes +12. What happens when I plug in a -1 for here? Same thing. positive 12 minus, what happens when we plug in a negative 1 here for this guy? This guy is always negative 4. This guy's not interesting. Everything you say, hi, f of x, y, what do you evaluate at any point? Negative 4. What do you evaluate at 114? Negative 4. It's a very boring person as a function. They're always evaluated for the same thing. So this becomes 1. So this becomes 144 minus 16, which is what, greater than 0? Our second derivative test says, okay, interesting stuff happens whenever your d of AB is greater than 0. All right. Now it is either a local minimum or local maximum. We don't know yet. We must now determine what is f of f double, the second order partial derivative of f in x evaluated at AB. Meaning, what is this? The sign of that is what determines whether we got a local minimum or local maximum. If that is greater than 0, we have a minimum. If that is less than 0, we have a maximum. So what is it? Well, that's this. So it's positive, so we have a minimum. So this is a minimum. Is that making sense? It's just follow the theorem, take partials. Oh no, I needed that. Last but not least, let's check what this one is. Okay, this is just 12. That's just 12 minus, this guy is always negative 4. So this becomes, what do we get here? Same thing. It's also a local minimum. Because the calculations followed the identical path. Okay? So, wow, that's it. I didn't get to cover as much as I wanted to. And that seems to be a common trend every class. We need to have 3-hour-long classes. Yeah, I know. I don't want that either, guys. Trust me. That's a complete joke. I'm 100% kidding. Okay. So yes, the test is not today, and the test will not be next week either. It'll be the week after that. Chapters 10 and 11. But we'll be moving on with the material. We'll be moving on to chapter 12 pretty soon. Oh my goodness, chapter 12. Guys, this is going to be really fun. We're going to be talking about multiple integrals. Yeah. Yeah, Jamie. I know. I can't wait either.